Welcome to Math, Week 7, Polynomial Operations. This is Module Math 1 on the Math Tutor Self-Study track. Today we have 10 practice problems at the end. This week we add, subtract, and multiply polynomials by hand. We drill the special product patterns including perfect squares, difference of squares, and the sum and difference of cubes. We also identify each polynomial's degree, leading coefficient, and standard form. By the end, you will see how loss functions and polynomial regression rely on exactly these mechanics. Phase A, Math Track. This video is sponsored by Subthesis. Visit subthesis.com to learn more. A polynomial is a sum of terms of the form a times x to the n, where n is a non-negative integer. The degree is the highest power. The leading coefficient is the coefficient of that highest power term. Both depend on writing the polynomial in standard form, which means descending powers. This week we cover the three core operations: add, subtract, multiply. Then we look at a small library of special product patterns you should memorize. After that, the machine learning connection, where polynomials show up in loss functions, polynomial regression, and characteristic polynomials of matrices. We close with the 10-question practice quiz and a recap. Let's dig deeper into what a polynomial actually is. A polynomial is an expression built from variables and constants using only addition, subtraction, multiplication, and whole number exponents. No division by a variable, no negative exponents, no square roots of variables. Polynomials are classified by the number of terms. A monomial has one term, like 5x cubed. A binomial has two terms, like x squared minus 4. A trinomial has three terms, like 2x squared plus 3x minus 1. Key vocabulary to lock in now. The degree of a polynomial is the highest exponent on the variable. The leading coefficient is the coefficient of the term with the highest degree. Standard form means the terms are written in descending order of degree. And here is what is not a polynomial. Expressions with negative exponents like x to the negative 2, or with variables under a square root, or with variables in a denominator. Those break the whole number exponent rule. 4. Polynomials are also classified by their degree, which gives them a name. A degree 0 polynomial is a constant, like the number 7. Degree 1 is linear, like 3x plus 2. Degree 2 is quadratic, like x squared minus 4x plus 1. Degree 3 is cubic, and degree 4 is quartic. The table on this slide shows each degree name alongside an example. Notice that the name comes from the highest power of the variable, not from the number of terms. Standard form is critical. It means writing terms in descending order of degree. For example, 5 minus 3x plus 7x cubed minus x squared is not in standard form. Rewritten in standard form, it becomes 7x cubed minus x squared minus 3x plus 5. Always reorder before identifying the degree or the leading coefficient. Adding and subtracting polynomials is just combining like terms. Like terms share the same variable raised to the same power. 3x squared and x squared combine to 4x squared. 2x and negative 5x combine to negative 3x. Constants negative 1 and 4 combine to 3. Done. Subtraction has one extra step. You must distribute the negative across every term of the second polynomial. 4x squared plus 3x minus 2 minus the quantity x squared minus x plus 5 becomes 4x squared plus 3x minus 2 minus x squared plus x minus 5. The minus flips the signs on all three terms of the second polynomial. Then, combine like terms to get 3x squared plus 4x minus 7. Let us walk through a complete addition example. We need to add 5x cubed minus 2x squared plus x minus 4 and negative 3x cubed plus x squared minus 7x plus 9. Step 1 is to identify the like terms. Group the x cubed terms together, then the x squared terms, then the x terms, then the constants. Step 2. Combine each group. 5x cubed plus negative 3x cubed gives 2x cubed. Negative 2x squared plus x squared gives negative x squared. X plus negative 7x gives negative 6x. Negative 4 plus 9 gives 5. Step 3. Write the final answer in standard form. 2x cubed minus x squared minus 6x plus 5. Always double check that your answer is in descending order of degree. Now let us work through subtraction, where the number one mistake lives. We need to subtract 6x squared plus 5x minus 3 minus the quantity 2x squared minus 3x plus 8. Step 1 is the critical one. Distribute the negative sign to every term in the second polynomial. 2x squared becomes negative 2x squared. Negative 3x becomes positive 3x, and positive 8 becomes negative 8. The rewritten expression is 6x squared plus 5x minus 3 minus 2x squared plus 3x minus 8. Step 2. Combine like terms. X squared terms. 6 minus 2 gives 4. X terms. 5 plus 3 gives 8. Constants. Negative 3 minus 8 gives negative 11. Step 3. The final answer is 4x squared plus 8x minus 11. Remember, the most common mistake in polynomial subtraction is distributing the negative to only the first term and forgetting the rest. Always flip every sign in the second polynomial. Multiplying polynomials is just distribution. Every term in the first polynomial multiplies every term in the second, and you combine like terms at the end. For two binomials, a useful mnemonic is first, outer, inner, last. On the expression x plus 3 times x plus 5, first gives x times x, which equals x squared. Outer gives x times 5, which equals 5x. Inner gives 3 times x, which equals 3x. Last gives 3 times 5, which equals 15. Add and combine the middle terms to get x squared plus 8x plus 15. For larger polynomials, say a binomial times a trinomial, this mnemonic does not apply, but the underlying rule does. Distribute systematically. Every term in the first polynomial multiplied against every term in the second. Then combine like terms. The work scales, but the principle is the same. Let us break down the first, outer, inner, last method step by step using the example 3x plus 2 times x minus 5. First means multiply the first terms of each binomial. 3x times x equals 3x squared. Outer means multiply the outer pair. 3x times negative 5 equals negative 15x. Inner means multiply the inner pair. 2 times x equals 2x. Last means multiply the last terms of each binomial. 2 times negative 5 equals negative 10. Now combine. We have 3x squared minus 15x plus 2x minus 10. The two middle terms, negative 15x and 2x, combine to negative 13x. The final answer is 3x squared minus 13x minus 10. Always remember to combine like terms at the end. Leaving 4 separate terms when 2 of them are like terms is one of the most common mistakes. There are 5 special product patterns you should memorize. They save time and reduce sign errors. First, the perfect square of a sum. The quantity a plus b squared equals a squared plus 2ab plus b squared. The middle term is always plus 2ab. Second, the perfect square of a difference. The quantity a minus b squared equals a squared minus 2ab plus b squared. The middle term is minus 2ab. Third, the difference of squares. The quantity a plus b times a minus b equals a squared minus b squared. The cross terms cancel. Fourth, the sum of cubes. A cubed plus b cubed factors as the quantity a plus b times the quantity a squared minus ab plus b squared. Fifth, the difference of cubes. A cubed minus b cubed factors as the quantity a minus b times the quantity a squared plus ab plus b squared. Notice the sign pattern flips in the trinomial factor. When you multiply a binomial by a trinomial, you cannot use first, outer, inner, last, because there are more than 4 products. Instead, distribute each term of the binomial across the entire trinomial. Our example is x plus 3 times 2x squared minus x plus 4. Step 1. Distribute x across every term of the trinomial. X times 2x squared is 2x cubed. X times negative x is negative x squared. X times 4 is 4x. Step 2. Distribute 3 across every term. 3 times 2x squared is 6x squared. 3 times negative x is negative 3x. 3 times 4 is 12. Step 3. Combine like terms. The x squared terms, negative 1 plus 6 gives 5x squared. The x terms, 4 minus 3 gives 1x. The final answer is 2x cubed plus 5x squared plus x plus 12. This same strategy works for any polynomial multiplication, no matter the size. Now let us apply those special product patterns to real numbers. Example 1. Perfect square of a sum. Expand the quantity 2x plus 3 squared. Using the pattern, a squared is 4x squared, 2ab is 12x, and b squared is 9. So the answer is 4x squared plus 12x plus 9. Example 2. Perfect square of a difference. Expand the quantity x minus 5 squared. A squared is x squared, 2ab is 10x, b squared is 25. Answer, x squared minus 10x plus 25. Remember the middle term is negative because we are squaring a difference. Example 3. Difference of squares. Expand the quantity 3x plus 4 times 3x minus 4. A squared is 9x squared, b squared is 16. Answer, 9x squared minus 16. There is no middle term because the cross terms cancel. The key insight is that memorizing these patterns lets you skip the full distribution process. That saves time and reduces the chance of sign errors, especially under test conditions. So why do polynomial operations matter for machine learning? 3 concrete reasons. First, loss functions. Mean squared error is a polynomial in the model parameters. When you expand and simplify that polynomial, you find the gradient, which tells gradient descent how to update the weights. Taking derivatives of polynomials is the first step. Second, polynomial features. In regression, you can create new features from existing ones by squaring them, cubing them, or multiplying them together. Expanding x plus 1 squared into x squared plus 2x plus 1 is literally creating polynomial features. scikit-learn has a preprocessor called polynomial features that automates this. Third, kernel methods. The polynomial kernel in support vector machines computes the inner product in a higher dimensional feature space without explicitly mapping the data there. The formula involves expanding the quantity x transpose y plus c raised to the power d. Understanding polynomial expansion is the foundation for understanding what that kernel does. Before we jump into the quiz, let us review the 4 most common mistakes I see with polynomial operations. Mistake 1. Forgetting to distribute the negative sign to every term when subtracting. Students often only flip the sign on the first term of the second polynomial. Remember, the minus sign applies to all terms inside the parentheses. Mistake 2. Squaring a binomial incorrectly. The quantity a plus b squared is not a squared plus b squared. You are missing the 2ab middle term. Always use the perfect square pattern. Mistake 3. Leaving out the middle terms in a difference of squares. When you have a plus b times a minus b, the result is a squared minus b squared. Students sometimes write a squared minus ab minus b squared, adding a phantom middle term. The whole point of this pattern is that those terms cancel. Mistake 4. Forgetting to write the answer in standard form. After combining like terms, always rearrange in descending order of degree. Standard form is how we identify the degree and the leading coefficient. Keep these traps in mind as you work through the quiz. It is practice quiz time. 10 questions covering everything we learned today. Adding, subtracting, multiplying polynomials, special products, and a connection to machine learning at the end. For each question, try to work it out in your head or on paper before looking at the answer on the next slide. Let us go. Question 1. Expand the quantity x plus 3 times x plus 5. This is a basic first, outer, inner, last problem. Take a moment and work it out. The answer is B, x squared plus 8x plus 15. First, x times x equals x squared. Outer, x times 5 equals 5x. Inner, 3 times x equals 3x. Last, 3 times 5 equals 15. Combine 5x and 3x to get 8x. The trap is forgetting to combine the middle terms and leaving 4 separate terms. Question 2. Expand the quantity x minus 4 squared. This is a special product, the perfect square of a difference. Think about what the middle term should be. The answer is C, x squared minus 8x plus 16. Using the perfect square of a difference pattern, a squared is x squared, 2ab is 2 times x times 4, which equals 8x with a minus sign, and b squared is 16. The classic trap is writing x squared plus 16 and forgetting the middle term entirely. Question 3. Expand the quantity x plus 2 times x minus 2. Look at the structure. What special product pattern applies here? The answer is A, x squared minus 4. This is the difference of squares pattern. The quantity a plus b times a minus b equals a squared minus b squared. The cross terms, plus 2x and minus 2x, cancel perfectly. The trap is adding a phantom middle term, writing x squared minus 2x minus 4 instead of the clean result. Question 4. What is the degree of 3x to the fourth minus 2x squared plus 7? Remember, the degree is determined by the highest power of x in the polynomial. The answer is C, degree 4. The highest power of x is 4 from the term 3x to the fourth. The polynomial is already in standard form because the powers descend, 4, then 2, then 0 for the constant. The leading coefficient is 3. A common mistake is confusing the coefficient with the degree, answering 3 instead of 4. Question 5. Expand the quantity 2x minus 3 times x plus 4. Show your work step by step. Use first, outer, inner, last, and make sure you combine like terms at the end. The answer is 2x squared plus 5x minus 12. First, 2x times x equals 2x squared. Outer, 2x times 4 equals 8x. Inner, negative 3 times x equals negative 3x. Last, negative 3 times 4 equals negative 12. Combine 8x and negative 3x to get 5x. The trap here is getting the sign wrong on the last term. Negative 3 times positive 4 is negative 12, not positive 12. Question 6. Expand the quantity x plus 1 times the quantity x squared minus x plus 1. This is a binomial times a trinomial, so you will need full distribution, not first, outer, inner, last. Look at the structure carefully. This connects to one of our special product patterns. The answer is x cubed plus 1. Distribute x across the trinomial. X cubed minus x squared plus x. Then distribute 1. X squared minus x plus 1. Combine. The x squared terms cancel, the x terms cancel, leaving x cubed plus 1. This is actually the sum of cubes pattern in reverse. The quantity a plus b times the quantity a squared minus ab plus b squared always simplifies to a cubed plus b cubed. Recognizing this pattern helps you verify your algebra instantly. Question 7. Subtract the quantity x squared minus x plus 5 from 4x squared plus 3x minus 2. Show each step. Remember the critical step. Distribute the negative sign before combining like terms. The answer is 3x squared plus 4x minus 7. Step 1. Distribute the negative. X squared becomes negative x squared. Negative x becomes positive x. Positive 5 becomes negative 5. Step 2. Combine like terms. 4x squared minus x squared gives 3x squared. 3x plus x gives 4x. Negative 2 minus 5 gives negative 7. The trap is only flipping the sign on x squared and leaving the other terms unchanged. Question 8. What is the leading coefficient of 5 minus 3x plus 7x cubed minus x squared? Be careful, this polynomial is not in standard form. Rewrite it first, then identify the leading coefficient. The answer is C, 7. First, rewrite in standard form by descending degree. 7x cubed minus x squared minus 3x plus 5. The leading term is 7x cubed, so the leading coefficient is 7. The trap is picking the first number you see in the original expression, which is 5. 5 is the constant term, not the leading coefficient. Always reorder first. Question 9. Add 3x squared plus 2x and x squared minus 5x. This is straightforward addition. Identify the like terms and combine them. The answer is B, 4x squared minus 3x. 3x squared plus x squared equals 4x squared. 2x minus 5x equals negative 3x. There is no constant term because neither polynomial had one. The trap is adding the coefficients of unlike terms. For example, adding the 2 from 2x to the x squared term. You can only combine terms with the same power of x. Question 10. This is a conceptual question. Why are polynomial operations foundational for machine learning? Match each machine learning concept to the polynomial operation it relies on. Take a moment to think about the connections we explored earlier in the lesson. Here are the connections. Loss functions like mean squared error expand to polynomial expressions that you need to minimize. Polynomial features use polynomial multiplication to create new input columns like x squared, x cubed, and cross terms. Kernel methods in support vector machines use polynomial expansion to map data into higher dimensions without computing the full expansion directly. Every time a machine learning model says it is fitting a curve, it is performing polynomial operations under the hood. Let us recap what you learned today. You can now add and subtract polynomials by combining like terms, and you know to distribute the negative sign first when subtracting. You can multiply binomials using first, outer, inner, last, and distribute across trinomials when needed. You recognize the 5 special product patterns, including perfect squares and difference of squares. And you understand how polynomial operations connect to machine learning through loss functions, polynomial features, and kernel methods. The biggest traps to remember: always distribute the negative to every term when subtracting. Never forget the middle term in perfect squares, and always rewrite in standard form before identifying the degree or leading coefficient. Next lesson, we flip the process. Instead of expanding polynomials, we will factor them. Factoring strategies include pulling out the greatest common factor, grouping, and applying special patterns in reverse, like factoring a difference of squares or a perfect square trinomial. This is the inverse of everything you practiced today. Thanks for watching. If you found this helpful, please like and subscribe. See you in the next lesson on factoring strategies.